So let's talk about the character of the solar wind. I mean, the solar wind is really a plasma. I think everyone knows that. It's mostly protons with a few percent helium and then trace amounts of other species like O6. And of course, it's got electrons too, and it's streaming at about 400 kilometers a second. Now, the density is about 5 particles per cubic centimeter, really not that much, but it's highly variable, both the density and temperature. And of course, the moon is an obstacle in this flow. And in fact, the moon interacts directly with the, the plasma interacts directly with the surface. Next slide. Now, just to give you an example of the variability, we know that there are extreme events, these coronal mass ejections. And they can send out a much denser plasma. They actually have about 1 billion tons of material. It's about 10 times the plasma density of nominal solar wind, and actually the heavy ions like He++ go from a few percent up near 20% and beyond during a solar storm. And again, these will impact the moon and affect the moon. Next slide. Now, prior to 2009, most people would have, if you thought about plasmas, you would have thought of them as a surface loss process, and that really has a lot to do with our previous work with the icy moons at Jupiter and Saturn, where really sputtering is really strong. And sputtering for 1 keV proton incident on something like the lunar surface, you'll get sputtering there as well. And sputtering really has 2 forms at 1 keV. One is momentum transfer, where simply the mass of the ion coming in ejects the material, but you also get a little bit of ionization. In fact, it was a little bit more energetic. You actually get a lot of ionization, but you get some ionization at 1 keV as well. Now, again, for ice, the yields for ice, I show that down there in the lower left-hand corner. It's almost 1 molecule release for every ion coming in. So it's really, sputtering really does wear down ice. For something like SiO2, it's a lot less. It's more of a collecting and implanting material, but where the yields are about 1 in 30. Next slide. But 2009 changed all this dramatically. And it looks like the slides here, my slides got rearranged here in this in the version that I'm looking at. But really, in 2009, there was this discovery of this mid-latitude, and I call it a veneer of OH in water. And these 3 great publications by Peters, Clark, and Sunshine talked about the observation of this IR absorption feature near 3 microns. And the Sunshine paper talked about this rather provocative measurement of a possible diurnal effect where the OH content maybe is reduced at noontime relative to mornings and afternoons. Next slide. Well, what are the possible sources for this nonpolar water? I think did my slides just disappear?
I'll get it right back up. Stand by.
Oh, okay. Yep. It looks like my webcam stopped as well. There we go. Oh, there we go. Good. So what are the possible sources for this nonpolar water? Well, Tom McCord wrote, I think, a great review. Actually, he had a great paper on the M-cubed results with new results in his work. But the front end, it was actually a terrific review, and he did actually talk about 3 possible sources. One is, of course, intrinsic mineralogy. The other possibility is cometary and meteoric infall. And the third is solar wind conversion. And as Larry Taylor said yesterday, it's probably a combination of all 3 at some levels. And I'm going to focus a lot on solar wind conversion. And again, this is not a new concept, as Tom said in his review paper, but we have to apply solar wind. When we do solar wind studies, we have to apply, there's a caution here, because solar wind, of course, is a destructive process as well. It can sputter and be a loss for any buildup of high concentrations of H. So there's sort of a yin-yang thing here. Next slide. And that kind of brings us to this next view of the contrasting nature of the solar wind surface interaction. And basically, it can do both. It can, in terms of how it manufactures or destroys water, actually has the possibility of doing both. Now, on the right-hand side, I show pathways where solar wind ions can be a source. You know, solar wind ions will implant, the H will be retained, and you'll form OH and maybe form water through recombinant desorption, like Michael Poston has talked about. Or if you have impacts, you know, sort of like a whole new chemistry experiment where the energy of the impact can maybe make OHs in the impact process. But we have to remember that there's also sputtering, there's also diffusive losses, and sputtering, if you had a high concentration of H's in your surface, will erode those H's, can get rid of superficial OH. There's this mysterious chemical sputtering, which I think no one really, you know, that can create losses. But, you know, I show an arrow sputtering, where sputtering can create adsorption sites, which actually then can collect water. So sputtering actually has a footprint in the source process. So if you look down at the bottom, we sort of think there has to be a set point or balance between the source processes and the loss processes. Next slide. So let's talk a little bit about the variables that control solar wind implantation. The first one is, of course, the incident flux. And, you know, Bob Johnson wrote a nice formula for the incident flux. We pretty much have an idea of what this is. On the day side, there's solar wind. On the night side, there seems to be a big void. And this void has been studied. In fact, it was some of the early work that I did on plasma physics, where there's this really big trailing wake behind the moon that goes back maybe 30 lunar radii. And Jasper Hellick's PhD thesis was actually looking at lunar prospector results, 6,000 orbits near 100 kilometers, and found that you know, solar wind densities can drop out by 1/500th of within the wake compared to what you get in the nominal solar wind. Now, I also have to mention that for a quarter of a lunation, we're also the moon's in the geomagnetic tail with a warmer plasma. I'm not going to speak to that today because we will barely. We can barely understand what's happening in the solar wind, let alone the more complicated, warmer plasma. But I just want to let you know that as well. Next slide. Now, one of the big variables, Ricky, next slide. Yep, one of the big variables that I think is underappreciated is diffusion. Once you implant, the H's can diffuse back out. And the diffusion time, or it can be thought of as sort of a proton residency time, and that residency time is a strong function of temperature. And what I show here in this figure from Dana is over the temperature range that you typically get at the equator region at the moon, your diffusion time can change by nearly 20 orders of magnitude. And so it's it's an exponential amplifier in some sense. And so at low temperatures, the protons will tend to, the word I want to use is loiter, just kind of hang around and form OHs. And of course, you may ask yourself, how many OHs can you form? Well, Starr-Kina in 2001 discussed that. It's really, if every O in the material in that top 100 nanometers formed OHs, you'd have a density of about 10 to the 28 per meter cubed getting in that top 100 nanometer interaction region. Next slide. But the thing that controls this implantation is the internal properties of the material itself, and that is especially defects. And Darby Dyer wrote a nice paper about that, really addressing that, and Starr-Kina talked about that as well. Basically, defects can both enhance trapping locations by providing vacancies. It can also, in some locations, enhance diffusion by creating defect channels back up to the surface. So what it will basically do is it can both retain but also allow some H's to escape out. But basically, if you have these disrupted lattices, you'll get these vacancies and possibly O's with unsatisfied bonds that again will be more reactive and create the OH. And we don't, we have samples. We know that this surface is disrupted by, I include a picture here of these amorphous rims. And they just, you can imagine, their crystal lattices have just all been destroyed in those rims. So the moon's material has the internal properties that would have this sort of defects. Also, when we think about this, we're also bringing in other elements of the space environment now as controlling variables. Things like impacts, radiation damage, and sputtering are all now part of the story of H retention. Next slide. Now, just to get into more details here on the internal reaction, Starr-Kina in 2006 talked about this diffusion. where the diffusion is a function of diffusion activation energy, U, where low values of U means that you can easily diffuse out, the high values of U means that your H's are trapped. So in a material with defects, you have this, I call it loitering of H's, where with defects, U's can have values greater than 1 to create trapping of the H's in vacancies. Really with defects, you'll probably get a range of values from low to high, particularly if you have channel type defects as backs to the surface, but we have high values of U in certain locations, you'll trap those H's. The other thing that Starr Kina talked about, which I thought was really great, was about once you get to the surface, the H just don't necessarily jump off the surface, but there's this process she calls inhibition. I love that. I kind of love that name. Where in order for H's to get off the surface, they actually have to migrate around and form H2s to then sort of hop off the surface as a molecular H. And in colder regions, inhibition isn't quite as active. There's as much migration as in hot regions. So what you could have, as she described in her paper, is you could have a buildup of H's near the surface because they can't jump off. Now, since 2006, this picture's been modified a little bit. People have found neutral H. And the group at Georgia Tech, particularly at higher temperatures, has talked about the possibility that OHs may migrate on the surface to form H2O, which then hops off the surface. So there's sort of variance of this, but there is that surface boundary issue that Starr Kina, I think, very astutely defined. And keep in mind, she's writing about this about 3 years before the actual observation of the water veneer in 2009. So, I mean, this is really quite a nice paper. Next slide, please. Okay, so we're talking about implantation, sputtering, defects, but let's not forget that sputtering is still active. It's still a loss mechanism, and in some sense, we don't suddenly throw out Bob Johnson's book just because we now think we see implanted material. The fundamentals still apply here, and there's a great example of that. There's a recent paper by Andrew Ichimura, which showed that implanting Ds both created OD, but could also sputter or at least cause the release of OHs. So he could see that 3 microns, the absorption feature, the 3 micron infrared absorption feature actually decreased, while at the same time he was getting an increase in the 4 micron OD absorption feature. So, the Ds were doing both, affecting loosely bound OHs, to use the parlance of Carl Hibbett's, the physi-absorbed OH, which is probably a contamination, which is why they went with Ds. But it created the ODs that you could see at 4 microns. So again, this punctuates that contrasting nature where, sort of the Ds giveth and the Ds taketh away sort of thing. Next slide. So let's create water now. Okay, so now we've been talking about OHs and forming OHs. To create water takes, in some sense, another step. Maybe something like impacts. Maybe something like recombinative desorption has been discussed by the Georgia Tech group, which again, as I mentioned before, may be a form of inhibition, where you have OHs and OHs on the surface to then make H2O. But once those waters start jumping around, as Carl and Michael talked about yesterday, they'll have these adsorption sites where the water will collect. And again, you would expect in the environment where you have impacts and sputtering that there'd be more actually adsorption sites in the material. And of course, all this stuff migrates and eventually gets to the polar region, as Dana has talked about back in her 2000 paper. So next slide. So to rack and stack these, I tried to make continuity equations. I think back in the wet versus dry moon, we talked about.
Still have 90 seconds.
Oh, okay. As we talked about in the wet versus dry moon, we talked about making these continuity equations, one for hydrogen, one for OH, and one for water. And this is what the hydrogen one would look like. This is what they would sort of look like with all their terms, with the source terms. What I'd like to do is focus on the first equation. Ricky, how about the next slide? If you focused on the first equation and assumed that you were in a steady state equilibrium and that you had a drier regolith so that there wasn't a lot of sputtering, you could actually compare sources and loss terms. And Ricky, let's go to the next slide. And that's something Dana Hurley did recently, where she found that that where the surface was warm, you would tend to have more diffusive losses and a less OH building up, whereas when you got into the cooler region, diffusion wasn't the dominant loss process. OH reactions tended to dominate, and you get a buildup of OH. Next slide. Okay, I think we'll skip that slide. Okay, so there's mounting evidence for a diurnal effect, sort of like what Dana has been talking about. Of course, there's Jessica Sunshine's paper where you actually saw the IR signature actually decrease at noontime compared to the larger solar zenith angles. But this afternoon, Amanda Hendricks and Tim Livingood and Greg Greaves are all going to talk about both observations and processes that all work on relatively fast time scales, like on less than the lunation time scale. So there's, and I won't say a whole lot about it here since I'm running out of time. Next slide. So where can the soil reactivity to make the OHs come from? Where do you get the high U values? Well, I show here our usual suspects in the space environment: impacts, high energy radiation, maybe triboelectric charging if you walk over a surface and start fracturing it. But impacts definitely, I mean, the Lunar paper that just came out last year showed an enormously high level of OHs in the agglutinates, which, so the products of the impact seem to collect OHs, and I think those H's might have even been of solar wind origin, according to that paper. Again, that in an agglutinate, you would expect that you've really disrupted the crystalline structure and created and have created these kinds of vacancies and all that where H's could collect. Next slide. So some fundamental questions that we still have, like is this reactivity an in situ phenomena, or does it become more reactive in situ? One big question is what happens to the OH and water superficial content after a coronal mass ejection passes, after a solar energetic particle passes, after a meteor shower, and possibly after an artificial release on the moon. You can imagine releasing heavy water, for example. And this, I would suggest that you might want to fly something like the next generation of M cubed. I think Carly talked about yesterday, M4. But have it up there during solar active periods, during solar maximum, and have it up where you might, during a time when you might want to do an artificial release, just to see how the space environment modifies this hydration process. Next slide. So to conclude, I think the key takeaway is that diffusion is really an underappreciated effect. And diffusion, defects, and the destructive space environment all seem to be kind of interconnected, or at least that's the kind of the narrative that I'm kind of working on here, where diffusion is controlled by defects, and those defects are in turn controlled by the space environment, like things like high energy radiation. So really H retention and maybe a sort of a systemic environmental effect. And one thing you have to ask yourself, and I had it in the, Vicki, why don't you go back to the previous slide for a second. One question I wanted to ask is there a hydrological Bode's law to these dry airless bodies? Like, for example, if you took the moon and took it out at 2 AU, you could somehow lasso it and move it out there, would all those differential continuity equations I had before, would they all come to a new equilibrium? The solar wind is less, but then the surface might be cooler, which would then retain the fewer H's that are being implanted. How would that look compared to moving the moon into, say, a half an AU? So is there as you move these bodies through the heliosphere, are there different equilibrium set points for the hydration and OH process? So I think I'm going to end this talk there, and I'm probably over. Hopefully, I'm not too far over.
Okay, I'm going to start reading the questions. First question we have is from Indu Varatharajan. Sorry. Does water formation lead to oxygen deficit on the surface?
That is a good question. I think the way I would say that is I don't know, but I would say it depends on the process. that you, you know, I mean, to do it further, you might expect that just by, you know, conservation of those, but, you know, it may depend on the process. And in some sense, if the water is bouncing around and, you know, it may be transported to another part of the surface, like in a polar crater. So it depends on how big you draw your volume in some sense. So I guess I don't really have a good answer other than to slide out of it by saying it depends on how big the volume of box you're looking at.
So before we get to the next question, can the next speaker please start sharing a screen and getting set up?
Okay. The next question is from Gordon Chin. How does the solar wind implantation and hydroxyl and water formation / diffusion scenario change in a highly porous surface?
Yeah, that's a good question. I mean, we didn't really talk about that at all. I mean, in some sense, we're really talking about what's going on, so in some sense, within the dust grain in, you know, 100 nanometer scale. What happens, you know, when you're really talking about fluffy, porous material? You know, I would suspect that whatever's going on gets in deeper. You probably have more sequestration because you probably have more shadowed regions. The plasma can get in, but the sunlight maybe can't. But that's a good question. I mean, I really don't know. It's a good question. I mean, I'm just speculating.